Astronomers thought they were tracking one interstellar visitor, 3I Atlas, the third confirmed object from beyond our solar system. Routine observations, expected trajectory, everything proceeding as predicted. But days ago, their telescopes picked up something no one anticipated. A new object, drifting between Earth and 3I Atlas, moving through space where nothing cataloged should exist. And it shouldn't be there. Initial reaction, instrument error, cosmic ray artifact, reflected light from known satellite. The standard false positives that plague astronomical observations. But successive observations from independent facilities confirmed identical results. The signal persists. The object is real. And its properties raise questions that challenge everything astronomers thought they understood about what we're observing in our cosmic neighborhood. The detection came from routine monitoring programs designed to track near-Earth objects and potential hazards. Ground-based facilities in Chile and Hawaii operating coordinated observation campaigns, multiple telescopes simultaneously imaging the same sky regions to improve detection reliability and reduce false positives. During one such coordinated session focused on 3I Atlas trajectory, analysis software flagged an anomaly. Unexpected light curve, brightness variation matching no known satellite signature, position inconsistent with cataloged asteroids, motion vector suggesting high velocity through inner solar system regions. Standard protocols demanded verification before announcement. Independent confirmation, eliminating systematic errors. Too many false alarms have embarrassed astronomy over decades. Reflections misidentified as comets. Instrument artifacts proclaimed as phenomena. Software glitches interpreted as genuine objects. So observers waited, gathered additional data, pointed different telescopes at coordinates, used varied instruments with different optical characteristics and detector sensitivities, ruled out mundane explanations systematically. And every observation confirmed the same conclusion. Something real exists at those coordinates, something moving, something previously undetected, despite decades of sky surveys that should have cataloged every significant object near Earth. The apparent brightness suggests relatively small size, certainly smaller than 3I Atlas nucleus, estimated at several kilometers diameter. But brightness alone provides ambiguous size information without knowing surface reflectivity. Dark objects appear fainter than bright reflective ones of identical dimensions. Composition matters enormously when converting observed brightness to physical size. More revealing, the velocity. Preliminary trajectory calculations indicate motion faster than typical asteroids at similar solar distances. Not escape velocity like 3I Atlas hyperbolic path, but faster than stable circular or elliptical orbits, characterizing most solar system bodies, suggesting either highly eccentric orbit or possibly another object not gravitationally bound to our stellar system. The Discovery team immediately recognized significance. This wasn't routine detection. This represented something genuinely unusual, requiring intensive follow-up observation and analysis. Comment below. What would you name this mysterious new object? Initial trajectory reconstruction revealed something immediately intriguing. The object's path shows partial alignment with 3I Atlas trajectory. Not identical, not following the same hyperbolic escape path exactly, but close enough to eliminate pure coincidence as plausible explanation. Imagine two aircraft flying roughly parallel courses, not in identical flight paths, not traveling same speeds, but clearly moving in related directions with similar headings. Close enough that connection seems probable, even if details differ. That's the geometric relationship astronomers observed. The rogue object travels through space in trajectory reminiscent of 3I Atlas, but with distinct differences in velocity, inclination, and exact path. Similar enough to suggest relationship, different enough to spark intense debate about what that relationship actually represents. Several hypotheses emerged immediately. First, and most obvious, fragmentation. Perhaps 3I Atlas shed material during perihelion passage when solar heating reached maximum intensity. Cometary nuclei often fragment under thermal stress, temperature gradients creating mechanical stresses, sublimation driving pressure buildups, structural weaknesses failing catastrophically. If fragmentation occurred, ejected pieces would follow trajectories similar to but not identical with parent body. Launch velocity from breakup event plus inherited velocity from parent creates paths that diverge gradually over time. Fragments initially travel together before separating as small velocity differences accumulate into large spatial separations. This would explain trajectory similarities perfectly. Fragment inherits most of 3I Atlas velocity and direction, but adds small component from ejection. Result, related but distinct path through solar system. But problems exist with simple fragmentation hypothesis. Timing appears wrong. 3. I-Atlas passed perihelion weeks ago during October 2025. Why would fragment only now become detectable in March 2026? Perhaps it was present earlier, but too faint against solar glare. Perhaps ejection happened post-perihelion from delayed outgassing rather than during maximum heating. Possible, but requiring additional assumptions. Alternative hypothesis, completely independent object. Perhaps another interstellar visitor arriving coincidentally from similar direction. Perhaps long-period comet from our own solar system's distant reserves with orbit that happens to align partially with 3I Atlas trajectory by pure chance. Statistical arguments make this seem unlikely. Space is vast. Trajectories are infinite in variety. Having two unrelated objects follow similar paths simultaneously requires remarkable coincidence. Not impossible, but improbable enough to make astronomers suspicious of invoking pure chance as explanation. Third possibility combines elements of both. Perhaps material released from 3I Atlas much earlier during its approach. Perhaps months ago, when the comet first entered inner solar system and began active sublimation at 5 astronomical units distance. Material released then would have traveled separate paths since diverging substantially from parent trajectory by now. Detection now simply reflects when that material reached position and orientation favorable for observation from Earth. Each hypothesis makes testable predictions. Fragment ejection predicts composition matching parent. Spectroscopy should show similar chemical signatures if material truly came from 3I Atlas nucleus. Independent object predicts potentially different composition reflecting different formation environment. Early release material predicts intermediate properties and possibly smaller particle sizes. Determining which hypothesis proves correct requires additional observations, better trajectory data, higher quality spectroscopy, possibly radar measurements if geometry permits. The scientific community mobilized rapidly to gather exactly this evidence. Subscribe now, because the spectroscopic data reveals something completely unexpected. When astronomers obtain spectra of the rogue object, results deepen mystery rather than resolving it cleanly. The spectrum faintly mirrors 3I Atlas, similar overall pattern. Same general features, indicating similar broad chemistry, carbon dioxide signatures, water-ice absorption bands, complex organic molecules. This similarity strongly supports connection between objects, suggests common origin, or at least formation, under similar conditions in similar stellar environments. Independent objects from unrelated sources would likely show different spectral signatures reflecting different formation chemistry. But subtle deviations exist. Small differences in relative abundances, slight shifts in specific absorption features, minor variations that could indicate real compositional differences, or might simply reflect measurement uncertainties and different observing geometries. Interpreting these deviations requires extremely careful analysis. Are they genuine compositional differences indicating the rogue object isn't simply fragment, but something more complex? Or are they instrumental artifacts and observational noise within expected measurement precision? One intriguing possibility: differential processing. Perhaps both objects originated from same parent body but experienced different subsequent histories. Maybe the rogue object represents surface material ejected early during 3I Atlas approach, material that spent months exposed to direct solar radiation and cosmic ray bombardment before detection. Surface processing could alter chemistry detectably while preserving overall similarity. This would explain spectral pattern perfectly, mostly similar but with subtle differences from radiation, weathering, and thermal processing. The slight deviations become evidence for extended, separate evolution rather than fresh, recent fragmentation. Alternatively, differences might indicate the rogue object represents compositionally distinct material from 3I Atlas interior. Cometary nuclei aren't homogeneous. They contain layers and regions of varied composition, reflecting formation conditions and subsequent evolution over billions of years. A fragment from nucleus interior would show chemistry different from surface material dominating main coma observations. This layered composition hypothesis predicts that continued observation might reveal evolving spectral signatures as the fragment's own surface erodes and exposes deeper materials with different chemistry preserved from formation. Third explanation involves measurement challenges. The rogue object is faint. Obtaining high-quality spectra pushes current instrument capabilities. Signal-to-noise ratios aren't optimal. Perhaps the apparent deviations simply reflect statistical noise in challenging observations rather than genuine compositional differences. Only improved data with better precision can resolve this ambiguity. Discovery timing raises intriguing questions that extend beyond pure astronomy. The rogue object appeared in data just weeks after SpaceX conducted Starship Flight 11 in March 2026. That test flight demonstrated advanced tracking systems and deep space observation capabilities designed explicitly for missions beyond Earth orbit. During that flight, Starship's instruments conducted observation campaigns targeting various celestial objects to validate sensor performance and data processing algorithms. 3I Atlas was among targets for these validation tests. The interstellar comet provided ideal test case: known trajectory, confirmed existence, challenging observation geometry requiring sophisticated tracking. Some analysts now suggest the timing isn't purely coincidental. Perhaps Starship observations detected the rogue object first. Perhaps advanced sensors aboard that test flight resolved signal that ground-based telescopes initially missed or dismissed as noise. Perhaps the discovery actually originated from Starship data that then prompted ground telescopes to search specific region where object was detected. If true, this would represent significant milestone. Commercial spacecraft contributing to fundamental astronomical discoveries. Private sector capabilities augmenting traditional observatory networks. New observation platforms providing complementary data that enhances overall detection and characterization capabilities. But official statements remain vague about exactly what Starship observed and whether its data truly contributed to discovery. Proprietary concerns and competitive considerations limit information sharing between commercial operators and academic astronomy community. Scientific researchers express frustration at incomplete data access that hampers complete analysis. Nevertheless, temporal correlation raises fascinating possibility that deserves serious consideration. Perhaps future Starship flights could be explicitly tasked with astronomical observation missions. Perhaps commercial spacecraft will increasingly contribute to solar system monitoring and discovery programs. Perhaps traditional boundary between astronomy and spaceflight blurs as capabilities advance and new platforms become available. This potential represents evolution in how astronomical research gets conducted. No longer purely ground-based telescopes and dedicated space observatories, but also commercial vehicles conducting observations opportunistically during test flights and operational missions. Crowdsourcing discovery across multiple platforms and operators, this detection carries significance far beyond simply adding another entry to object catalogs. If the rogue object truly originated from 3I Atlas, it provides unprecedented opportunity to study interstellar material more directly than ever before possible. Main cometary nuclei are difficult observational targets. Active sublimation creates bright comas that overwhelm faint signals from solid surfaces. Dust and gas surround nucleus, making direct observation extremely challenging. Spectroscopy samples material after it's been processed by sublimation and solar radiation, rather than pristine interior composition. But fragments potentially offer different observation, geometry, and conditions. Smaller pieces might be less active. Sublimation might not completely obscure surface properties. Perhaps we could observe relatively unprocessed material if fragment composition differs from heavily active surface regions of parent nucleus. This would deliver closest thing to direct sampling currently possible without actually sending spacecraft to collect and return physical samples. Remote spectroscopy of fragment surfaces potentially reveals chemistry more representative of bulk composition than coma spectroscopy achieves for main nucleus surrounded by active sublimation. Understanding how interstellar objects fragment also matters enormously for multiple reasons. Do they break apart easily under modest thermal stress, or remain structurally coherent until extreme conditions? What does fragmentation behavior reveal about internal structure and mechanical properties? These questions directly inform our understanding of how material formed around other stars differs from local solar system objects. Fragmentation mechanics also affect hazard assessment for any future interstellar visitors that might approach Earth more closely. Knowing whether objects tend to fragment or remain intact influences predictions about atmospheric entry and potential ground impact scenarios. But if the rogue object didn't originate from 3I Atlas, implications become even more profound. Then we may have detected fourth interstellar visitor, another object from beyond passing through our cosmic neighborhood simultaneously with 3I Atlas. Statistical evidence that interstellar objects are substantially more common than previously estimated from detection rates. Current confirmed detection rates suggest perhaps one interstellar visitor every few years. But selection effects bias this severely downward. We detect only brightest, largest, or most active objects. Smaller, darker, less active visitors pass completely undetected. True population probably exceeds detected numbers by factors of hundreds or thousands. Every additional detection improves statistical constraints on actual population, helps astronomers estimate how much interstellar material constantly flows through our solar system unnoticed. informs predictions about future discoveries and optimal search strategies for finding additional examples. Astronomers worldwide are coordinating intensive observation campaigns targeting the mysterious object. Multiple facilities observing simultaneously, gathering optical photometry, detailed spectroscopy, and possibly radar data if object passes close enough to Earth for radio telescopes to detect returned signals. Immediate priority, refining trajectory with much greater precision. Current orbital solutions remain preliminary with substantial uncertainties. Additional observations over coming weeks will constrain path more definitively. Determine whether it truly follows escape trajectory, like 3I Atlas, or remains gravitationally bound in some extended solar system orbit. Trajectory refinement also reveals origin more definitively. If calculations trace it back to spatial proximity with 3I Atlas during perihelion passage, fragmentation hypothesis strengthens considerably. If backtracking shows independent approach from different direction entirely, that indicates separate interstellar origin or possibly origin from solar system's distant comet reserves. Spectroscopic campaigns will continue gathering higher quality spectra with better signal-to-noise ratios, extended wavelength coverage spanning ultraviolet through infrared, multiple observation geometries as viewing angle changes, looking for temporal variations that might indicate rotation or compositional heterogeneity across surface. If spectral evolution occurs over time, that provides crucial clues. Changing signatures might indicate progressive surface erosion, exposing fresh material beneath weathered exterior, or thermal processing as solar distance changes, affecting surface temperature and sublimation rates, or rotation, bringing different surface regions with varying composition into view. Each possibility constrains physical properties differently. Some astronomers advocate for radar observation if geometry permits favorable conditions. Radar provides direct distance measurements with extraordinary precision impossible from optical observations alone. Also characterizes surface roughness and potentially detects internal structure through echo delays from different depths within object. But radar requires objects to pass relatively close to Earth. Current projections suggest rogue object might not approach closely enough for radar detection, but trajectory uncertainties leave this possibility tentatively open. Looking further ahead, could this object become spacecraft flyby target for future mission? Probably not immediately, given long timescales required for mission planning and development. Mission design requires years of preparation. Launch windows depend on precise trajectories. Current uncertainties preclude serious mission planning at this stage. But if object remains observable for extended period and proves sufficiently scientifically interesting, future mission proposals could emerge within next decade. A new object drifts through space between Earth and 3I Atlas. Faint signal in telescope data that might represent fragment from interstellar visitor, or might be something completely independent. Trajectory, suggesting relationship but spectroscopy, showing subtle differences that complicate simple explanations. Astronomers work systematically to solve this puzzle, gathering additional observations, refining trajectories, analyzing spectra with increasing precision, testing hypotheses against accumulating evidence. The mystery deepens as data accumulates, and simple answers remain frustratingly elusive. This is how astronomy advances in practice, not through sudden revelations, but through patient accumulation of observations, building understanding gradually from incomplete information, revising hypotheses as new data arrives, embracing uncertainty while working systematically toward greater clarity. The rogue object reminds us that our solar system still contains surprises, that even in space near Earth, objects exist that escaped detection until recently, that our surveys remain incomplete despite decades of systematic searching, that discoveries await those patient enough to look carefully at data others might dismiss as instrumental noise. Did it break away from 3I Atlas during perihelion heating, or does it represent something entirely separate, arriving from different origin? The answer matters enormously for understanding interstellar visitor population and fragmentation behavior. Comment below. Do you think this broke away from 3I Atlas, or is it something new? Subscribe for updates as observations continue, as trajectories refine with additional data, as spectroscopy reveals more about composition and potential origin, as mystery gradually resolves into understanding or potentially deepens into something even more intriguing than current hypotheses suggest. Whatever this object represents, it's teaching us that space between stars isn't empty void. Material travels constantly. Chemistry from one stellar system can appear in another through natural processes operating across cosmic timescales. Our cosmic neighborhood receives constant delivery of samples from beyond that we're only now developing capability to detect and characterize properly. The search continues. The mystery evolves. And somewhere between Earth and 3I Atlas, a small piece of cosmic material drifts through darkness, carrying secrets about its origin that observers on Earth are working systematically to decode